Welcome to the frontier of science. Today, I'm taking you on an incredible journey into the heart of quantum mechanics. We're about to unveil the single mystery the great Richard Feynman spoke of, the double-slit experiment. This seemingly simple experiment literally rewrote the rules of reality, defying our every intuition. Get ready to question everything you thought you knew about matter, space, and time. It all begins in 1801 with Thomas Young. He wanted to understand, is light a wave or a particle? Newton thought it was made of corpuscles, but Young showed light behaved like a wave, creating an interference pattern. But then, in the early 1900s, Einstein arrived with photons, particles of light. And here's the chaos. Is light a wave or a particle? The question extended to all subatomic matter. Quantum mechanics was born. Imagine shooting tiny balls like bullets at a screen with two holes or slits. What would you expect to see on the screen behind? Two distinct bands, right? One for each slit. This is what happens in the classical world. If instead of balls they were waves like those in water, we'd see an interference pattern with clear and dark stripes. But with electrons, something crazy happens. Even shooting them one at a time, the pattern that forms is an interference pattern, as if every single electron behaved like a wave and interfered with itself, passing through both slits simultaneously. And here's the twist. If we try to spy on the electron by putting a detector to see which slit it passes through, the interference pattern disappears. Two bands appear, as if the electron had decided to behave like a particle. This is wave-particle duality. Matter and energy are not just waves or just particles, but both, depending on the circumstances. But why did the electron change behavior or nature? What process regulates this transition? Let's try to understand it together. This leads us to two key concepts: superposition and wave function collapse. Before measurement, a particle doesn't exist as we're used to seeing it in the classical world, but exists in a superposition of all its possible states. It's as if a single electron passes simultaneously through both slits. Its nature is described by a wave function that describes all these probabilities. Think about it. This very ability to exist in multiple states simultaneously, to be here and there at the same time, is the basis of the revolutionary power of quantum computers. But when we measure, the wave function collapses, and the particle chooses a definite state, so the electron passes through only one slit, just like a classical particle. And here arises a huge dilemma, one of the greatest mysteries of quantum mechanics. What happens to the discarded states during this collapse? Where does the energy or information of all those other possibilities that the particle didn't choose go? The Copenhagen Interpretation simply says it just happens. There is no underlying causal explanation, but this answer doesn't satisfy everyone. Indeed, many other interpretations try to make deeper sense of this phenomenon, such as Bohmian mechanics or many-worlds theories. And this is where Hugh Everett's many-worlds interpretation comes in. This theory proposes that the wave function never collapses. Instead, every time a measurement occurs, the universe divides or branches into as many parallel universes as there are possible outcomes. In one, the electron passed through one slit, in another, through the other. All the discarded states don't vanish, but continue to exist in other branches of reality. A fascinating vision, but one that leads us to an infinite number of universes. The double-slit experiment didn't stop there. Physicists continued to push the limits, creating variants that revealed even more astonishing aspects of reality, such as experiments with larger particles. Wave-particle duality is not exclusive to photons and electrons. Scientists have demonstrated interference for increasingly massive particles. Think of fullerene molecules, the famous buckyballs, composed of 60 carbon atoms. They were passed through double slits and, just like electrons, showed interference patterns. More recently, Quantum interference has been observed with even more complex organic molecules, composed of hundreds of atoms and with masses exceeding 10,000 atomic mass units. The challenge is ever greater because the larger the particle, the more sensitive it is to interaction with the environment and loses its quantum coherence. This shows that quantum physics is not just for very small things, but is the basis of reality, even if at a macroscopic level the effects are hidden. Proposed by physicist John Archibald Wheeler, this experiment challenges our idea of time and causality. A photon is fired towards a first beam splitter that puts it in a superposition of two paths. The decision on how to measure the photon, whether to reveal its path or allow it to interfere, is made after the photon has already passed the first junction. This is possible using very fast devices that change the experimental configuration in a very short time. The results are clear. The photon's behavior depends on the measurement choice, even if this choice occurs in our future relative to when the photon was at the junction. If we decide to know its path, it behaves like a particle from the beginning. If we decide not to know, it behaves like a wave and interferes. It seems the future can influence the past. This challenges our intuition of linear causality, suggesting a universe where past, present, and future are interconnected in surprising ways. This experiment uses entangled photons, meaning particles whose properties are intrinsically correlated regardless of distance. A special source like a nonlinear crystal creates pairs of entangled photons. One, the signal photon, goes towards the double slits. The other, the idler photon, its twin, takes a different path. To destroy the interference pattern of the signal photon, its path is marked. For example, polarizers in front of the slits give the photon a specific polarization depending on the path. This marking, while not a direct spy, makes the path information potentially available, and, predictably, the interference disappears. And now the twist. We act on the idler photon, the entangled twin. Another polarizer is used to erase the path information of its partner. Incredibly, correlating the results of the two detectors shows that the interference pattern on the signal photon detector is restored. This demonstrates that the availability of path information makes the interference disappear. If this information is erased, the wave nature reemerges. This variant shifts the concept of the slit from space to time. Special materials are used, like a thin film of indium tin oxide, whose optical properties can be modified in fractions of a second by ultra-short lasers. Instead of two physical slits, two temporal slits are created where the material allows light to pass only at two very specific and close moments. The interference pattern does manifest as a change in the frequency of light, altering its color. This means the photon, temporally extended, passed simultaneously through two moments in time, interfering with itself. Further proof that our spatial and temporal intuitions don't hold in the quantum world. These experiments force us to rethink everything. They haven't just shown strange phenomena, but have revealed that our familiar reality is just the tip of the iceberg. There's a hidden reality beneath, governed by rules that completely subvert our way of perceiving the world. Linear causality, time flowing only forward. Perhaps these are just intuitions of our macroscopic world. At the quantum level, experiments suggest that past, present, and future might be interconnected in nonlinear ways, where events are more correlated than we think. Our perception of a unidirectional flow of time could be an illusion, an emergence from a deeper, non-local level. And what about materialism? Quantum mechanics has shaken its foundations. The idea of an objective and deterministic reality, independent of observation, has been radically questioned. The main mysteries that remain open are: how does wave function collapse occur? And where do the discarded states of superposition go? These questions continue to fuel the debate and push research towards new interpretations. It doesn't mean materialism is dead, but that it must evolve. We talk about inclusive materialism, which recognizes emerging complexity and the irreducibility of certain levels of reality. The scientific community has accepted quantum mechanics for its incredible predictive effectiveness, while continuing to debate and explore its deeper interpretations. The double-slit experiment continues to inspire research. From quantum computing, which harnesses superposition and entanglement to create powerful computers, to quantum biology, which investigates the role of quantum effects in biological processes, up to research on the very foundations of reality. This experiment is not just a physical phenomenon, but a window into the deepest mysteries of the universe. It reminds us that reality is far more complex, fascinating, and strange than our minds can easily conceive. If this video made you think, leave a like, subscribe to the channel, and let me know in the comments what you think. See you in the next video, always at the frontiers of science.